And welcome back. Today we're going to look at Dalton's law of partial pressures and concluding up chapter 5. We already looked at gas laws and density of gases, and now we're going to look at how each gas within a mixture of gas contributes to the overall pressure of that gas. And so the air you breathe is a blend of nitrogen and oxygen, carbon dioxide, water vapor, and a whole host of other gases in smaller amounts, and each of these gases is exerting a pressure because it does have mass and it is being pulled down by the gravity of the earth, so it has a force, and that's being distributed over a certain area. So the total atmospheric pressure then is the sum of all of these pressures within that mixture of gases, and the pressure that each gas exerts is termed a partial pressure according to Dalton's law of partial pressures. The pressure of a mixture of gases is the sum of the partial pressures within the different components, where total pressure, PT, equals to P1 plus P2 plus P3 plus however many gases that are out there, meaning that the total pressure within a gas is equal to the sum of the pressure contributed by each individual gas within the mixture. So the pressure of a gas in a given volume and at a specific temperature really depends on the quantity of the gas, not the identity of the gas, but the quantity of the gas. Remember the ideal gas law, where PV equals nRT, where P is for pressure, V is for volume, N is the number of moles, R is the constant, and T is temperature in Kelvin. Now M is not even a factor there, no mass, just the number of moles in. Now granted, mass does have a little bit to do with the number of moles, but it is not a factor, as this is just a number of moles present. So mass doesn't play any role in the pressure of a gas, just the number of moles. So in a gas mixture, we can consider the behavior of each gas separately. So let's look at a mixture of three gases, gas A, gas B, and gas C. So there are in A, number of moles in A, meaning that the number of moles in gas A is in A. And there is in B, number of moles in gas B, meaning that the number of moles in gas B is simply in B. And the number of moles in gas C is going to be denoted as NC. So that the total number of moles within this mixture of gas is going to be Na, or the number of moles contributed by gas A, plus the number of moles contributed by gas B, plus the number of moles contributed by gas C, or Na plus Nb plus Nc. Total number of moles equals Na plus Nb plus Nc. So this gas is contained in a given volume at a given temperature, where the pressure contributed by gas A times the volume of the gas is equal to the number of moles of gas A times the constant times the temperature of the entire mixture. And also that the pressure contributed by B is equal to pressure contributed by B times V equals NBRT, and the same with gas C. The pressure contributed by gas C times V equals the number of moles of C times R times T. So using Dalton's law with these substitutions, we get total pressure of the gas mixture equaling the pressure contributed by gas A plus the pressure contributed by gas B plus the pressure contributed by gas C. And when we do some Dalton substitutions into this equation, we see that the number of moles in gas B times V over RT does equal to PA, or the pressure contributed by gas A. the number of moles in gas B times the volume divided by RT equals the pressure contributed by gas B, and the number of moles in gas C times V over RT equals the pressure contributed by gas C. So what we've done is substituted these values for this value using the ideal gas law, such that the total pressure becomes this equation. Now, because the number of moles of the gas is a coefficient or constant, it can be pulled out, so that Na plus Nb plus Nc is all being multiplied by V over RT. So then, the total pressure in a mixture of gases is given by total pressure, P total, equals the total number of moles times V over RT, which is what we have here. Total number of moles times V over RT. Once the total pressure is determined, defining partial pressures can be done with the help of the mole fraction. And what is a mole fraction? It's fraction of a mole. Ha! What we're going to do is define the mole fraction as the letter X. And the mole fraction is the ratio of the number of moles of a particular gas in a mixture to the number of total moles in the mixture. That sounds a little confusing, so let's go over what it is. So that gas A's mole fraction would be, mole fraction A is the number of moles of A divided by the total number of moles. Or here, number of moles in A divided by the total number of moles. So in that mixture of A, B, and C, we have number of moles in A plus number of moles in B plus number of moles in C. And we're looking at A's contribution, so that is A's mole fraction, X of A. B's contribution would be the same thing, only with B on top. Number of moles of B divided by Na plus Nb plus Nc equals the number of moles of B over the total number of moles. That gets you X's mole fraction, or X's contribution to the total number of moles. And C's mole fraction, X sub C, looking at the number of moles contributed by C divided by the total number of moles. Now, when we combine this with the equations above, we're going to yield a partial pressure for gas A in the mixture, such that the pressure, partial pressure contributed into this mixture of gas by A is equal to the mole fraction of A times the total pressure. And when we apply that to the other gases in the mixture, we get the partial pressure of gas B equals the mole fraction of B times the total pressure. The partial pressure of gas C within the mixture equals the mole fraction of C times the total pressure of the gas. So this is Dalton's law. Partial pressure is equal to the mole fraction of that particular gas times the total pressure of the gas mixture. Let's look at an example. Halethane has a formula C2HBrClF. This is a non-flammable, non-explosive, and non-irritating gas that's commonly used as an inhalation anesthetic. Put you to sleep. Now, let's suppose we're mixing 15 grams of halethane vapor with 23.5 grams of oxygen gas. So I've got two gases within a mixture of gases. If the total pressure of that gas, the mixture, is 855 millimeters of mercury, what's the partial pressure of each gas? In other words, how much does halethane contribute to this 855 millimeters of mercury, and how much does oxygen contribute to the 855 millimeters of mercury? Now, we don't know the volume or the temperature of the mixture, But what we can do is use the mole fraction to calculate partial pressures, because we know how much the molecular weight is of each of these gases. We're given a formula, so we can calculate the molecular mass or molecular weight of halothane, and we know the molecular weight of oxygen gas is 32 grams. So we can calculate the number of moles. Therefore, we can use the mole fraction and multiply it by the total pressure, and we'll be able to determine the partial pressure of each gas. So when adding up the molecular weight of halothane, we see that we get a molecular weight of 197.4 grams. So 15 grams of halothane is going to be 0.076 moles. That's taken by dividing 15 by 197.4. So the number of moles of the first gas, halothane, in this mixture is 0.076. Now, 1 mole of oxygen we know is 32 grams. And 23.5 grams when divided by 32 gives us 0.734 moles of oxygen. So now we have the number of moles of halothane and the number of moles of oxygen. And when we add those together, we will have the total number of moles in this gas, or in total. Adding them together for in total gives us 0.810. So now we need to determine the mole fraction for halothane. Halothane's mole fraction is going to be the number of moles of halothane, we calculated as 0.076, divided by the total number of moles in the gas, 0.810. Put that in your calculator and we're going to come up with 0.0938. So this is halothane's mole fraction within the gas. Now the mole fraction for oxygen gas, XO2, we saw that the number of moles of oxygen was 0.734 divided by the total number of moles, 0.81, and that's going to give us a mole fraction of 0.906 for oxygen. So there we have our halothane and our XO2. When we multiply this by the total pressure, we should get the partial pressure for each contributing gas. Now remember, the total pressure is given as 855 millimeters mercury in the problem. So the pressure contributed by halothane, or the partial pressure contributed by halothane, is going to be equal to mole fraction of halothane times the total pressure. Remember, our mole fraction was 0.0938. Multiplying that by total pressure, 855 millimeters mercury, and we get a partial pressure of 80.2 millimeters of mercury. That's the contribution by halothane to the total pressure of the gas. Partial pressure for oxygen is the mole fraction of oxygen times the total pressure. We determined that the mole fraction for oxygen was 0.906. So multiplying that by the total pressure, 855 millimeters mercury, will give us oxygen's contribution to the total pressure, or oxygen's partial pressure. And oxygen's partial pressure, when you put that in your calculator, turns out to be 774.8 millimeters mercury. Now, you want to make sure that your total pressures are equal to 100%. We get into rounding. These numbers, when we round and multiply, they may not come out to add up to 100%. In other words, these numbers have to add up to 855. If they don't, you're missing some pressure. So if they don't add up exactly, go back and look at how you've rounded it, either up or down, and and adjust for that so that they do. My numbers didn't exactly, so I adjusted this one to 0.8 and this one to 0.2 so that these work out nicely. So it has to add up to 100%, or you've lost some gas somewhere. All right, let's look at another example. Now suppose we mix 15 grams of carbon dioxide with 1.2 grams of hydrogen gas. If the total pressure of this mixture is 550 millimeters mercury, then what is the partial pressure of each gas in the mixture? So what is the pressure contributed by carbon dioxide, and what is the pressure contributed by hydrogen gas if the total pressure is 550 millimeters mercury? So starting with carbon dioxide, we know that 1 mole carbon dioxide is 44 grams. So we can determine the number of moles of carbon dioxide by looking at how much is present, 15 grams. So 15 divided by 44 gives us the number of moles in carbon dioxide, or 0.34. Now we can do the same with hydrogen. 1 mole of hydrogen gas, remember this is hydrogen gas, so this is a diatomic molecule. That's why I said these were important. We're talking about hydrogen gas. That's hydrogen in nature and thus diatomic. And since H has a atomic weight of 1, H2 must have a molecular weight of 2 grams. So 1 mole of hydrogen is 2 grams. So 2 divided by, 1.2 grams divided by 2 grams gives us a number of moles for hydrogen gas at 0.6. So figuring our total number of moles, adding these two together, 0.34 and 0.6, gives us 0.94 moles for a total number of moles. Now we need to determine the mole fraction for each gas. Mole fraction of carbon dioxide is going to be the number of moles carbon dioxide divided by total number of moles. So the number of moles of carbon dioxide we calculated at 0.34. Total number of moles, 0.94 moles. And divide those two out. Thus the mole fraction for carbon dioxide is 0.36. Now the mole fraction for hydrogen gas is going to be the number of moles of hydrogen gas present, 0.6 moles, divided by the total number of moles, 0.94. And that leaves us with 0.64 when we put that in the calculator. Now remember from the problem, total pressure was 550 millimeters mercury. So now we can, using this and the mole fraction, we can calculate the partial pressures of each gas. So partial pressure of carbon dioxide is going to be equal to the total pressure times the mole fraction for carbon dioxide. The total pressure was 550 millimeters mercury, and the mole fraction was 0.36. So the partial pressure of carbon dioxide in this mixture of gas is 198 millimeters mercury. Partial pressure of hydrogen is going to be the total pressure of the gas times hydrogen's mole fraction. So 550 millimeters mercury times 0.64 will give us the partial pressure of hydrogen, which is 352 millimeters mercury. Make sure these add up. That's a 0, that's a 5, and that's a 5. 550. So within this 550 millimeters mercury, carbon dioxide contributes 198 millimeters mercury, and hydrogen contributes 352 millimeters mercury. Okay, now it's your turn to work a problem. You walk into a room that has air that is nice to breathe. We all like to breathe, don't we? And it is a mixture that contains 63 grams of nitrogen gas and 18 grams of oxygen gas. And let's say we're at sea level, so the total pressure is going to be 1 atmosphere. That's just another term for pressure. So don't get freaked out by it. It works the same way as millimeters mercury in the examples. Just use this as your total pressure. What is the total pressure of each gas? That should say what is the partial pressure of each gas. I'm sorry. I should correct it, but I'm too lazy to go back and start this video over. This should be partial pressure of each gas within this mixture. So remember that nitrogen is going to contribute to the 1 atmosphere and oxygen is going to contribute to the 1 atmosphere. So go ahead and try your hand at working this problem. Have your teacher go ahead and push pause so that you can work this problem. Or if you are viewing this at home, push pause so you can go ahead and work this problem. When you are finished, press play and finish the lecture. All right, let's go over the solution to this problem. As before, we look at nitrogen to determine its molecular weight. Since there are 2 atoms of nitrogen in nitrogen gas, nitrogen has an atomic weight of 14, nitrogen gas has a molecular weight of 28 grams. So 1 mole of nitrogen gas is 28 grams. Thus, to determine the number of moles of nitrogen, we take how much is present, 63 grams, and divide it by the value of 1 mole. So we have 2.25 moles of nitrogen gas in this mixture. 1 mole of oxygen, if you remember, is 32 grams. So determining the number of moles of oxygen is taking what's present, 18 grams, dividing it by 32. And that yields 0.563 moles for oxygen gas. So with this, we add these together to get the total number of moles. 2.25 plus 0.563 gives 2.813 as a total number of moles. Once we have the total number of moles, you can determine the mole fraction for each part of the gas. Mole fraction for nitrogen is the number of moles of nitrogen divided by the total number of moles. In your calculator, that should give you 0.8. Number of moles of oxygen is, the mole fraction of oxygen is the number of moles of oxygen divided by total number of moles. That in your calculator, you should get 0.2. Remember, the total pressure was 1 atmosphere. So we can determine the partial pressure of each gas now that we have the mole fraction and the total number of moles. So the partial pressure of nitrogen gas is equal to the total pressure times the mole fraction for nitrogen. Total pressure was 1 atmosphere. Mole fraction for nitrogen was 0.8. That worked out pretty awesome. See, you didn't even have to calculate it. Partial pressure contributed by nitrogen is 0.8 atmospheres. Partial pressure for oxygen is equal to the total pressure of the gas mixture times the mole fraction for oxygen. So the total pressure is 1 atmosphere. Mole fraction is 0.2, and that one works out pretty nice too, leaving you with 0.2 atmospheres as a partial pressure contribution by oxygen. All right, let's look at now molecular speeds. The speed of a molecule within a gas is dependent upon the temperature of the gas. Remember that temperature is the measure of velocity of the particles within a compound or gas. Now, because the temperature is the measure of the amount of kinetic energy within the gas, and kinetic energy is 1/2 mv squared according to physics, and that kinetic energy is proportional to temperature, meaning the higher the temperature, the higher the kinetic energy or velocity. then we can say that 1/2 mv squared is equal to c times t, where c is constant, proportionality constant c. Now after we do some substitutions and manipulation, we come to Maxwell's equation, where r is now expressed in different SI units or metric units. And we have what's called the root mean squared speed of particles within a gas, or the root mean squared. So the RMS speed of particles within a gas is equal to the square root of 3 times RT over M, where R is a proportionality constant, and that proportionality constant is 8.314 joules over Kelvin mole. Write that down on your constant sheet if it's not there. Now, M is the molar mass in these calculations. And if we use kilograms per mole instead of grams per mole for molar mass, the kilogram will cancel out with joules. A joule is a kilogram meter squared over second squared. So if I use kilograms here, and I have kilograms up here in joules, those will cancel out nicely and leave us with meters per second squared, which turns out to be meters per second when you take the square root. So let's remember that. And here's a sample problem for RMS speeds. Calculate the RMS speed of oxygen molecules at 25 degrees Celsius. Now we know the formula is RMS speed is equal to the square root of 3RT over M for molar mass. Now here's what's known in the problem. We know that constant R is 8.314 joules per Kelvin mole. And the temperature is the temperature in Kelvin. So 25 degrees plus 273 gives us 298 K. And M is the molar mass. Oxygen molecules of oxygen gas, the molar mass of oxygen gas is 32 grams. Remember we said we wanted that in kilograms so that would cancel out with this value of joules in R. So converting this to kilograms is simply dividing by 1,000. So the molar mass of oxygen gas in kilograms is 0.032 kilograms. Now when I plug these values into the equation, I have 3 times 8.314 joules per Kelvin mole times the temperature, 298 K, divided by 0.032 kilograms. So the kelvins will cancel, and the joules, kilograms and kilograms here will cancel. Such that we have 2.32 times 10 to the 5th kilogram meter squared over kilogram second squared. I know somebody who's smart alecky back here in the back is going, what about mole right here? Well, it's left out of this. The molecular weight of oxygen is 0.032 kilograms per mole. And that will flip up here and cancel that out. I didn't put that in there, but if you're wondering where it went, this is actually kilograms per mole, so that goes away. Now when we take the square root of this whole thing, remember kilograms have canceled, meters per second will come out, and the square root of 2.32 times 10 to the 5th is 482. So the velocity then of these RMS speed or RMS velocity of oxygen molecules at 25 degrees Celsius is 482 meters per second. Well, I was going to say this is your turn, but it looks like I laid it all out there for you. So let's go ahead and just go over this. Calculate the RMS speed of nitrogen molecules at 40 degrees C. So with our formula, RMS speed equals square root of 3RT over M, where R is 8.314 joules per Kelvin mole. Temperature in Kelvin is 40 plus 273 gives 313 Kelvin. Now the molecular weight of nitrogen gas is 28 grams or 0.028 kilograms. So plugging that into the equation, we end up with 3 times 8.314 joules per Kelvin mole times 313 Kelvin divided by 0.028 kilograms per mole. Now when we multiply across and divide, we're going to get 2.8 times 10 to the 5th kilogram meter squared over kilogram second squared. So kilograms will cancel. Meters squared over seconds squared will come out as meters per second. And the square root of 2.8 times 10 to the 5th is 528. So the RMS speed of nitrogen molecules at 40 degrees Celsius is 528 meters per second. Okay, that about sums up this lecture. There's going to be some homework on partial pressures and molecular speeds posted soon, if not already. So go ahead and download that and begin working on those problems. And if you have any problems, let me know. See you next time.